To an inexperienced engineer, an above-ground storage tank is a static steel cylinder, defined entirely by its plate thickness. In reality, a tank is an interdependent, dynamically loaded system. The fluid, shell, foundation, and venting mechanisms act as interlocking, load-bearing elements. Removing or altering any single component compromises the entire structure. If one control fails, the remaining systems cannot compensate for the load. Engineering integrity requires more than a one-time design formula. It demands active management through a continuous life cycle. Modern management follows a 9-stage cradle-to-grave framework, from initial concept to retirement. Every stage inherits assumptions from the one before it. Changes in fluid or throughput can invalidate the original design basis. This process is a closed loop. Step 7, in-service inspection, resets the operating envelope. To manage these assets safely, we must deconstruct how flawed operating assumptions and hidden degradation lead to failure. Treating a dynamic, environmentally exposed asset as a static pressure vessel is the root cause of catastrophic, entirely predictable failures. No single document governs a tank's life cycle. Between structural design, fire protection, and maintenance, the regulatory environment is a dense web of interacting codes. This chart organizes the architecture into 3 lanes: new build construction, protection and safeguards, and in-service integrity. A strict line separates mandatory codes from recommended practices. API 650 dictates the construction of new vertical tanks, while API 653 controls the asset once it is in service. Above all of these consensus standards sits the ultimate override authority, the jurisdiction. Regulators like OSHA and the EPA enforce legal requirements that override owner preferences, industry consensus, and even the manufacturer's own guidelines. This complexity creates the legacy spec trap, where engineers rely on institutional memory instead of verifying current code additions. API Recommended Practice 545 for lightning protection provides a clear example. It has been officially withdrawn and is no longer maintained. Copying the phrase "comply with API 545" into a 2026 project specification mandates an orphaned standard, tying a mere asset to a framework that has been discarded. To prevent this, every variable, from fluid density to flow rates, must be formally frozen and approved before a single plate thickness formula is calculated. A tank built to an outdated recommended practice or a legally overwritten standard is non-compliant from the day it is commissioned. With the design basis locked, we can look at the physical geometry of the tank. This selection screening map shows that roof choice is more than a simple code decision. Vapor pressure is a factor, but engineers must also weigh emissions regulations, product cleanliness, and fire strategy when choosing between fixed and floating roof designs. This anatomical layout reveals how loads and degradation converge at specific interfaces. It illustrates the fundamental rule for inspectors: metal fails where geometry changes. Liquid head causes hoop stress to rise with diameter, forcing the lower shell courses to carry the highest hydrostatic demand. Consequently, the highest risk zone for the entire asset is the shell-to-bottom joint and the annular region. This corner handles multiple converging loads. Hydrostatic pressure pushes the shell laterally, thermal expansion creates shifting, and the structural weight of the tank pushes down. Standard ultrasonic testing grids often miss these interfaces entirely. They measure the center of the plate while leaving the most critical margin uninspected. Under full load, these geometric margins face immense physical force. A tiny, uninspected flaw here can tear a steel plate off its foundation. Inspection strategies must prioritize the shell-to-bottom joint, nozzles, and compression zones. Physical forces exploit the margins, not the middle of the plate. The vulnerabilities at the bottom go beyond structural stress. The bottom plate is simultaneously attacked by 2 independent corrosion systems operating on opposite sides of the steel. Product side corrosion is driven by sludge and water settling on the floor. This top-down pitting is managed through internal inspections, water draw-offs, and linings. Soil side corrosion attacks from the foundation up. It remains completely invisible from the outside of the tank until the plate is fully perforated. If a soil side breach occurs, product releases into the subsoil long before a visible leak develops, creating an environmental liability that can exceed the cost of the tank. To mitigate this, many owners install a double bottom to provide an engineered interstitial volume for leak detection. This creates the credit trap. An interstitial leak detection port that has never registered fluid fails to prove the floor is sound. The port could be blocked, or the fluid could be pooling in a different zone. Relying on a lack of data to calculate remaining life, without verifying the cathodic protection or the drainage design, is a failure of engineering logic. Even with sound steel, the ground beneath the tank can fail. Edge settlement is the most damaging geotechnical failure. As local foundation pockets sink, they drag the tank wall down, localizing extreme shear strain directly onto the critical shell-to-bottom weld. Relying on passive safety features or uninspected subgrades without active, skeptical verification is indistinguishable from guesswork. This lifecycle model integrates physical threats with jurisdictional standards. Step 7, Inspect and Assess, is the anchor. Inspection challenges the original math. Routing physical findings back to Step 2, the engineer reevaluates the design basis against the actual measured condition. A tank designed flawlessly decades ago can become dangerously non-compliant today if the operational throughput or hazard profile changed. This leads to the final mandate, the handbook's governing rule. Never apply a generic thickness, inspection interval, or settlement limit. Every variable must be tied by a competent engineer to the actual tank, measured condition, and active jurisdiction. Asset integrity management requires the discipline to evaluate the data, the code, and the physical margins, and know exactly when the only rigorous answer is to retire the asset entirely.